again, I used to play CTF. I'm busy now. I used to work at Intel on system software fuzzing until they paid me to leave the company. So I'm not here representing any employers, which is kind of fun. I do hobby hacking. I do side projects, all that good stuff. And I'm not a Windows person. So until like last week, when I started working on this stuff, I had like touched no Windows internals or anything like that. So it was entirely new to me, which was kind of fun. And you can find me on most websites at NovaFacing if you're interested in that. All right, so I was working on a fuzzer. That's what I was here last year to talk about. It fuzzes UEFI, it fuzzes Windows kernel, it fuzzes Linux kernel. And it's going great. I was using it. I was finding some bugs and stuff. I gave it to some engineers, and they were able to find some bugs and stuff too, especially like on the UEFI and Linux kernel side, which was great. It's, built on a simulator, so decently fast. We're talking like 5 executions per second. That's actually quite good, unfortunately. And everybody was pretty happy with it, except when it came time for me to use it on a bunch of projects. When I said, "Ooh, I kind of just want to work on the fuzzer. I don't really want to actually go try and find any bugs. That's not really my thing right now." And so I, tried to continue working on the fuzzer. So what I did was I just handed the tools to all of the developers and said, "You guys have your Windows kernel applications and drivers and stuff. Go ahead and find your own bugs." And they said, "We don't really like that." Because that's how I was giving everybody information on coverage for their Windows kernel drivers. Now, like technically, you can get everything you need out of that. It's got program counters, and it tells you what the program counter is at every branch. And if you look really hard, you can say, all right, this one comes before this one, so we must have this control flow. But nobody really likes doing that, especially not when you're fuzzing with like 100 harnesses on a super complicated driver. It's just not very fun. It turns out that there's a good way to do that, and it's coverage visualization. So if you've ever done like development on Windows or Linux and run a program and needed to do like performance testing on it, you've probably seen something like that graph on the right. That's a flame graph. It just tells you like this function executes for X% of your runtime of your program. So if your decoding function or your sorting function is running in like O of n cubed time, maybe you should make that a little more efficient because you were really lazy when you wrote it the first time. This one on the left is a little uglier. So that's actually the output of Clang's coverage metrics, and it tells you how many times each branch executed. But that's kind of ugly. It's not actually, in my opinion, like it's a level above the JSON, but it's not like 3 levels above the JSON to where most people would want to look at it. So we kind of want to aim for something more like the one on the right, a little bit more GUI based, a little bit easier for people who are used to working in Visual Studio and things like that to use. So we have a few options. We can use LVM's profile data or profile raw, whatever the format is that you're using. And that's omitted very easily. You just run a couple of, you compile with a specific flag, you run your program, it outputs a couple of files, and then you run this LVM coverage show, which will give you that kind of nice output on the right. It tells you how many times each line of code executed. It'll highlight ones in red if they didn't execute at all. So that's the kind of information we're after, but we're trying to support everybody with this. So not everybody is super comfortable in the command line. Not everybody is able to use LVM for their software, especially on Windows. That's a big thing. A lot of people are restricted to using Microsoft's compilers. So this isn't a perfect solution, but it's getting close. One problem with this as well, if we're trying to build this format into tools, is that this format has no specification. You have to just go into the LVM code base and read it all and say, all right, what's this weird binary format that tells me what the coverage is? It's not like incredibly complicated. It's like numbers and lines and stuff. But it's not super maintainable if every time LVM changes it, you need to go and look at the diff of a bunch of source code instead of just looking at a changelog on a document. So that's not super great. But it does have all the information we want. So basically what we're after is number of times each line executes, whether a line executed at all, how many times each branch was taken or not taken in our program. That includes like loops and if statements and stuff like that. And then LVM has this interesting one, which is modified condition decision coverage, which tells you for all of the like separate predicates in an if statement or a while condition, how many of those actually influenced the decision of the branch? And it turns out this is not that useful for development purposes, but it's very useful for security testing purposes, because you can tell what variables in the program are not getting flipped or are getting flipped to affect your control flow. So if you can say, all right, this particular variable is never getting modified to influence the direction of this branch, maybe we need to add some fuzzing or a test case that does modify it and see what happens. So that one's super useful, but not a whole lot of documentation about it. So there's another tool for the GCC suite of stuff, and obviously this won't really help us on Windows because nobody serious, unfortunately, is using like MSys2 for their development at work. But they have a couple things that are a little bit nicer than LVM's system. Very similar stuff, almost exactly the same compile command to add the instrumentation that you need to output this data. You run the program again, it produces a couple of binary files, and then you run this gcov format, which actually in this case produces a readable file, but it's basically just the text of the code output. So we're slightly better than LVM in that respect. We know what the format looks like, and it's probably not going to change. It's just code with a couple of annotations on it. But we're still not quite to a format that we can really use and output. So it turns out there's a tool that actually runs after gcov called lcov. I don't know what the L stands for. If somebody knows, feel free to raise your hand. But basically what this does is it's mostly intended for translating the gcov data to HTML. And we're getting back to our key objective of reaching a GUI, where basically we'll translate this to HTML, and then you can just view it as a web page, and you get a pretty output of all of your code with everything highlighted. Nobody has to run anything in a terminal. It's all platform independent. You just send somebody something, they open it in Chrome. So super nice. You just have a very simple text format. That's over here on the right, and then down at the bottom is the annotations of what all of those records mean. But it tells us almost all of the same stuff as the LVM and GCC coverage data. It tells us all of the branches we hit, all of the lines we hit, how many times we took each branch, how many functions have been covered, how many functions are not covered. The only thing it's missing is that MCDC stat, which theoretically you could add to this, but it's not in the specification. And theoretically you can also calculate from this if you work really hard. So I basically said, all right, that'll do. We'll use that. And our next task is to integrate into our fuzzing tool while it's executing and have it be able to observe what's happening when the program runs and output this format so that people can view this instead of anything in their terminal. So same example as before, but this is a web page that you can bundle up and send to somebody. It tells you all of the line coverage, function coverage. Not pictured here is like for each directory, it'll give you a list of functions as well, and then that's recursive. So if you have a code base, super huge code base, you can navigate through it easily, figure out what your spots all of your fuzzers are missing are, figure out what spots they're hitting, maybe variables that aren't covered, and so forth. So shop this around to a few Windows developers. They said, this looks great, please do it. So that sounds good. But we kind of need something to work with this format. The official code base for it is written in Perl, which I personally don't really like or understand or know in any way. So I wrote a little library for Rust, which I do like, and is also the language the fuzzer I was working with was written in. And we were good to go. That took like 4 hours. It's such a simple text format that it was pretty low effort. So we've got a library to work with lcov files in memory and then write them out to disk and then translate them to HTML. So basically what the fuzzer knows is the program counter of every edge. And in the program, when you're executing, if you hit a conditional statement, you have an edge. And one edge goes to usually the next instruction and one edge goes somewhere else. So if you have an if statement, it'll have the body of the if statement, or you'll jump down to below the body of that if statement. It kind of depends per assembly language, but in general, that's what the fuzzer knows, and that's basically it. It just gets that program counter stream and also the information of whether this program counter is an edge. So to go from program counter to a source line of code in this, obviously, once we've compiled the program and stuff, we don't have source lines necessarily. So we need to find an offset, which is the program counter minus the base of the object loaded in memory. So that'll be your ELF file, your PE file, whatever the case is. And we use debug info, either from the program or separately, which is usually the case on Microsoft platforms, to figure out what that base address and offset is. So we know what address we're at in the code. Debug info stores usually just a mapping of address to symbol, or like base of address and size usually is what it actually is, and then you can figure out what the offset is. So the way we get that on a running Windows system that's running in a virtual machine is via virtual machine introspection. Basically, we reach in using whatever mechanism our hypervisor or simulator in this case gives us, and we ask for some memory contents or the value of a register, and then we use that a bunch of times to figure out where the internal Windows structures are, and then we use that to figure out where all of the objects that we have the debug info for, but we don't have their base address, are located. So let's talk about how to do that. So in the simulator that I was working with, and in most like hypervisors or system emulators like QEMU, you'll be able to read virtual memory. You'll be able to read sometimes, but not always, physical memory, because that physical memory is simulated or emulated. And you'll be able to usually read registers. Now, with QEMU, sometimes you can't read all registers. Things like virtual machine extensions and all of the registers for that are usually not emulated. They're passed down to the host operating system through KVM or something like that. So you don't necessarily have the ability to read all registers, but for our purposes, we'll just assume that you can. And on the simulator, this fuzzer I was working on was built on, we could also read MSRs, or model-specific registers. So on Intel and AMD platforms, there's like thousands of these model-specific registers, and they hold super specific stuff, like since the last time you read this register, how many system management mode interrupts happened. So things that you don't frequently need access to, but the system has some value in storing that data, and sometimes Intel sees value in allowing you to know what that register's value means. So that's basically model-specific registers. Some of them are super commonly used. So we'll talk about one in particular that's used for this. So we kind of have a roadmap for what we need to do using this capability. First, we need to find the kernel, because if we don't know where the kernel is, we're going to have a really hard time finding all of its structures. And we're mostly worried about kernel drivers for this, and kind of less so user space processes. User space processes coverage is kind of already solved, like we looked at with those compile flags, and MSVC has its own way to do that, even though it's a little bit less easy to access. So first, we need to find the kernel, and I did not know how to do this. All I knew was how to read some memory, same thing as the simulator knew. So I started by looking at some existing tools. A lot of people here probably, maybe show of hands, know about volatility. Okay, decent number. So volatility is a memory forensics tool. So if you capture an image of the RAM from a running system, you can use volatility to basically ask questions about it, like was some malware active in this system when I dumped the RAM? Or what were all of the command line programs that were running, and what were their arguments when I dumped the RAM of this system? So to do that, it does a very similar thing to what we need to do. It scans through memory, it finds the kernel, it analyzes all of the structures of the kernel to find all of the information that it's able to give you. For the command line program example, it'll scan through memory until it finds the list of processes that's currently loaded. It'll traverse through those processes, and each process in Windows has a member of its internal structure that says, here was the command line arguments to this program. So just read those, dump it out, and now volatility has told you what the command line arguments are. So I looked there first because I took a memory forensics class in college and I knew about it. And basically the way volatility finds the kernel is by scanning the entire dump of RAM for just like a pretty simple signature of what the kernel is supposed to look like. And for my purposes, this was not good, because the simulator I was working on took like 2 or 3 minutes to scan through all of memory, and making it worse, the simulator let you put an arbitrary amount of RAM into the system. So like you could have a petabyte of RAM in your virtual simulated system, which would take a I didn't try this, but like 16 gigabytes took 2 minutes, so you can kind of do the math on how long a petabyte would probably take. But I needed it to be able to work for any amount of RAM, so this was not going to be good. But the thing I learned from that is kind of what the signature of the kernel looks like, and how to tell, like, if you have an address, is this address the base of the kernel? And we'll talk a little bit about that later. But the next thing I checked was libVMI, which was written by one of my coworkers and friends at Intel. And basically, this does the same thing. And I was a little bit miffed at this because libVMI is supposed to be used online. It's on a running system, but libVMI is designed to be used in a hypervisor like Zen or KVM, where reading memory is actually pretty fast. There's no emulation behind the memory. It's just go look at a physical address on the system you're already on. That's a pretty quick operation, and so they can kind of get away with doing that. So that still didn't work, but I compared the implementations of like checking whether a certain address is the kernel between libVMI and volatility, and I said, all right, these are pretty similar, so this must be the right way to do it. So again, a little bit of information gained, even though this didn't really work for my purposes. And then there's a third way to do this, which everybody online, if you search this problem, will suggest that you use, which is to just call ntquery system information, which is a function in NTDLL on Windows, which will just give you the base address of the kernel for free, which usually isn't something that you get access to on Linux, so I was a little surprised about that. There's some permission stuff involved. You know, you can't do this from every process. You need certain privileges, but that's cool. The only problem is, since I am the simulator kind of in this situation, I'm not actually allowed to run code on the system that's being simulated. So this still didn't work, but another piece of information gained: A, you can do this, which is kind of crazy, and B, this function will give you a lot more than just the base address of the kernel. It'll give you like process offsets, process information, where certain things are located, and so kind of just learning from all of the options. This is like a very large call. It has a lot of parameters. And so just kind of learning the vocab of what all of the internal structures of Windows were from the documentation for this function was also super helpful for just Googling stuff to complete the rest of this project. So I didn't know anything about Windows. I learned a little bit about like what the kernel maybe looks like. I didn't really know what a PE file looked like, so like learning the signatures for that was good. So where do we go next? I've kind of asked the security community by reading through their GitHubs. I've kind of asked the security community by messaging my coworkers, but it turned out that like he had some copyright thing on libVMI, so he couldn't really tell me much about it at work because he didn't want to lose his copyright. So lots of silly roadblocks, you know. It turns out that game hackers love the Windows kernel. And if you've ever played Call of Duty, you probably know this because there are just a million hackers everywhere. And of course, not all of them are kernel hackers. Most of them just downloaded stuff that they paid like $35 for online to cheat in video games, which I still don't understand. But the people who made those exploits know a lot about the kernel because they need to circumvent anti-cheat. Anti-cheat, for those of you who don't know, runs with like the maximum system permissions, usually on Windows. It can read everything you're doing. It can write to any process. It can download every picture you've posted of your dog from online if it wanted to. I don't know who decided it was a good idea to trust game developers who, you know, very frequently have bugs where you like walk through walls or roll through the ground in Mario 64 if you've watched the Half-A Press video. Yeah, I guess we do that. And it turns out that people who want to circumvent those anti-cheat things know a lot about the kernel because those kernel level privileges that the anti-cheat has need to be targeted by the game hackers so they can get around them. And so game hackers know a lot about like internals of Windows, all of the structures and stuff. So there's this website, unknowncheats.me, where people will just post full exploit code for like various versions of Windows. It's pretty fantastic. And they usually either won't attach any comments to it, or all of the comments will need to be Google translated, but you can get some good information out of this stuff. So like all of the structs that they use, I didn't know any of these, but they'll define all of the structs in their code. And the reason they do this is because these structs are not the in any header file that Microsoft publishes. Sometimes they're in PDB files that Microsoft publishes, which is debug info for Windows, and nobody really knows whether that's intentional or not, but some of these structs have been unintentionally published. Some of them have been reverse engineered and just kind of understood over time. But those structs kind of coming from the cheats websites were super duper useful for understanding like where all of the pointers that I needed to get to the process list and the kernel module list, which are really the two things we're after, were located. So there's also a couple other good places that I found to get info. So this guy, Jeff Chappell, I have no idea who he is. I didn't read the bio. I just went straight for the kernel struct documentation part of his website. But it's like probably some of the best documentation I've ever seen. So even if you don't care about like Windows structures, if you just want to learn about how to write documentation for structures for a program, I highly recommend checking out this website. It's like mind-blowingly good. And he claims that he's never worked for Microsoft. He doesn't know anything about these internal structs other than just like public knowledge and stuff, and he just works from that. But basically he describes every field in detail, its entire history of what it's ever done for just about every Windows kernel struct that I needed to use for this. So thank you, Jeff, if you're in the room. And then finally, the one thing Jeff doesn't do is publish like a machine-readable specification of all of these structures across time. I didn't really care about like working for Windows 7 or Windows XP or anything like that, but I really wanted to work for every version of Windows 10 and 11, just because we have lots of machines running those at the moment, and usually if you're testing kernel modules, you're probably on like the latest couple years of releases. Although I realized the other day Windows 10 was released in like 2015, so that's almost a decade, which is kind of crazy. So there's this project, Virgilius project. I forget where they got the name, but it is on the homepage because I remember reading about it. And basically what they do is they've taken all of those accidentally or on purpose, we don't know, published PDB files from Microsoft, and they've extracted all of the structure definitions from those, ingested them into YAML, which was an interesting choice. I don't know why they chose it, but they're all in YAML, and posted it on their website, which is super helpful. Because the first thing I tried to do before I discovered this website was download an ISO for every version of Windows ever. Spoiler alert, some of them are very hard to find. Unpack all of them, which is like 30 terabytes. I have that much storage, but I had to clear out some Linux ISOs to make room for the Windows ISOs. And then extract all of the PDBs myself by downloading them. And that's actually where I got stuck, because that is a lot of bandwidth. And it was going to take like 2 months to download all of it, which was not really cool with me because I started writing this talk like 3 weeks ago. So anyway, I downloaded the YAML. So the first thing I had to do was translate this YAML. I did not want to work with it. I don't really like YAML personally. I don't know how everybody in the room feels. If you're a Kubernetes person, you're probably either like really cool with it or really not cool with it, depending on which like side of the Kubernetes spectrum you're on. But I like writing Rust, as I mentioned earlier. And right now, they're in this weird like C definition in a YAML file. So the first thing I did was translate all of that to C from the Rust, because it was in C. It was just also in YAML. And then, of course, if you try and compile that C, it's not going to work because you have a bunch of structs defined later, which are part of structs defined earlier. And it turns out there's a very simple way to solve that. You just topologically sort all of the types, which actually is where the YAML came in handy, and I suspect maybe why they used it. So I have to give them a little bit of props, even though I'm still confused. After that, you've got C that compiles with maybe like 1 or 2 manual tweaks because there's some typos, but I was actually pleasantly surprised that I was able to just compile this C code like with GCC on Linux from like automatically extracted Windows structs. It was pretty cool. And then, of course, because Rust is awesome, we just have a tool that you can run that'll translate that all to Rust. You don't need to do any manual work. So that's kind of what that looks like. Here's the YAML on the left, very ugly. Here's the C in the middle, okay. And there's the Rust on the right side, which is beautiful. All right, so I mentioned that I needed every version of Windows earlier, and the reason that I do is because every time you have a new version of Windows, like for whatever reason, and I'm not sure why they did this, all of these fields get shifted, resized, reordered, and this will be like between build versions. So like Windows 21.1 has like 3 or 4 builds, and all of them, the structures that you need to do this to are like completely different. And so in order to resolve that in the simulator, you need to be able to figure out what version of Windows you're looking at so that you know what version of the struct you're looking at so that you know what the heck you're looking at. So first thing we need to do is check the Windows version, and thankfully this is very easy. And Microsoft, I really hope, never changes it. So there's a structure, and this one doesn't change that much, which is good. Like, fields at the bottom of it change, but the fields we care about have never moved, which is great. And I learned that from Jeff Chappell's website, so one of the reasons you should check it out. There's this struct called kuser shared data, and it's always mapped at the exact same virtual address in every address space while Windows is running. So any process or in kernel mode, you read this address, you're getting kuser shared data. And from that, you can get the major version, which is right now always 10, the minor version, which is right now always 0, and the build number, which is the thing you actually care about. And that'll tell you which version of Windows 10 or 11. Major version is 10 for 10 and 11, which is a little confusing, that you're looking at. And I figured that out by just running a bunch of Windows systems and looking at this struct in all of them, because people said stuff online, but I've been burned before by just reading unknowncheats.me and running code from it, so I just wanted to make sure. So we read that struct, we get the build numbers, and now we know what version of every other struct we're going to be looking at. So we build that into our system. Next thing we need to do, now that we know like what the kernel structures are and what their fields are and how big they are, is we need to actually find the kernel base. And so to do this, I think I already mentioned, we don't want to scan through all of memory. We could, but it'll take a very long time, and it might take a very, very long time. So what we want to do instead is find some code pointer into the Windows kernel, and we want to just scan backwards in memory, and I have a diagram of this. We want to just scan backwards in memory until we find the base of the kernel using those signatures that I extracted from libvmi and volatility3 and didn't write myself until I realized that I needed a couple more checks because, oh, it's not on this slide. Oop, sorry, we'll get there soon. All right, so there's 2 ways we can do this. One is the interrupt descriptor table. So on all, and this is x86 specific, so I apologize to the ARM enthusiasts in the room, but I haven't looked at ARM Windows yet. But there's this thing called the interrupt descriptor table, which tells the processor anytime an interrupt happens, you go to this table, and depending on what the interrupt was, there's a bunch of function pointers for you to run depending on what the interrupt is. So general protection fault, you run this, this particular function which handles that. Or divide by 0 error, you run this other function. And you can set these all to the same function, which will effectively give you like a single entry point for handling interrupts. Or you can set them all to different functions so that you just handle them one by one, depending on what that interrupt is. Now, this interrupt descriptor table, as of like one of the Windows 10 builds that I'm forgetting, it's like 19 something, Windows has introduced a feature called Kernel Virtual Address Shadow, KVAS. And basically what that does is they're trying to move any pointers that used to be into the code section of the Windows kernel into a different section in memory, which is sometimes adjacent to the kernel and sometimes not adjacent to the kernel. Although, as we'll see, it kind of doesn't matter for our purposes, but for like finding ROP gadgets and stuff, it really does matter. And that new code section is just called KVAS code, and that's, like I said, either located adjacent to the kernel or kind of near it, but separated by some memory range. So the second way, which actually doesn't work anymore, and that's why we're not going to use it, but it's worth mentioning, is the MSR II32 kernel GS base always points to a specific structure called the KPCR. And that KPCR contains a bigger structure, it's just tacked onto the end of it actually, called the KPRCB, kernel processor control block. And that contains a pointer to the current kernel thread. And so of course, if you can access the kernel thread, you would think there's probably like a reference to the entry point of whatever that kernel thread program is. And that used to be true and is no longer true. There's now no code pointers from that K thread into actual code of the kernel. So you have some like data from the kernel, but you don't have a code pointer anymore, which is unfortunate because that's actually a really nice way to do it, because it'll just give you a direct pointer into a known place in the kernel. And now we just have to find some known place in some memory that's not the kernel and try and find the kernel based on it. Luckily for us, it turns out that's not actually that hard. And this is kind of what either of those processes look like. If we take the IDTR, which is the interrupt descriptor table register, the base field of that register basically just straight up points to the interrupt descriptor table wherever it is in memory. So that's very easy to find. That'll work on like QEMU. Any simulator essentially has to have that IDTR. And then the second method, using the IA32 kernel GSBase MSR, that'll point to the KPCR, and then the IDT base field of that structure points to the same place as the IDTR. So if you were in a situation where you could only read MSRs, but you couldn't read the IDTR, you could at least still find the IDT from that first method. Or sorry, from the second method, if you could only read MSRs, which I don't think anybody else will ever end up in that scenario, but if you do, now you know how to do this. All right, so once we've found the first entry of the interrupt descriptor table, that's going to be divide by 0, actually, is the first entry of that. So we'll take the code pointer to the handler for that, which is a kernel system call called KI divide error fault. And this used to be in the kernel. It would just call straight into the kernel code at that location. Now all handlers externally, entry points into the kernel, are in this KVAS code section, which has like a swap.gs instruction to like change the page mappings, and then it'll jump to the actual handler in the kernel. So unfortunately, that means we would have to like disassemble that handler to figure out what its code pattern is that it's jumping to in the kernel. We would need to use we'd need to single step over that swap.gs instruction to get a new page mapping so that we could translate the addresses correctly to find the kernel. It's just kind of a mess. And so what we do instead is we just walk backwards in memory, because we know there's going to be some memory between KVAS code and the kernel code, but it's not going to be massive. And so we can pay a small performance penalty for a lot of simplification of this process by just doing what's called a scan back. And the unknown cheats people love this. There's like 100 different code examples of how to do this, and they all do it the same way and seemingly don't realize that 100 other people have posted the same code. So on versions below 19,000, pages are 4 kilobytes aligned, and on above 19,000, they're 2 megabytes aligned, which I think is large pages, but not huge pages, if I'm remembering correctly. So we have a start, that's our KVAS code pointer. We have a step, and now we need an end. So this is kind of the tricky part, is making sure that we'll go far enough with our scan, but we're not going to, like, for some reason, if we've picked a bad code address, we're not going to like go all the way to the 0 address, because then our system would walk backwards for like 20 minutes, and then it would say, all right, we reached null, so clearly there's an error. We probably want to fail a little faster than that. So our stop address, we basically just truncate our start address to like the nearest gigabyte and assume that'll probably be good enough. And so far I haven't seen it fail on any amount of RAM, so I think that does work. So, yep, once the page we look at is the kernel base, then we're good. We found the kernel. So that's really the hard part. But how do we know? Oh, yeah, here's the code for that. Probably nobody cares about this, and it was like 11 p.m. when I put this in the slide deck. But it's pretty simple. So we just take a build number for the kernel, and then get the IDT base, scan backwards, and check if page is kernel. And that's kind of the part that I took out of volatility and libVMI. So we basically just do a bunch of checks, and if any of them fail, then it's not the kernel. And if we get to the bottom, then we're good. So first we make sure it's a PE executable. That's kind of the first check. And then if it is a PE executable, we make sure it's also an NT executable. Because it turns out that Microsoft, for one reason or another, I don't know if this is on purpose or not, has put a bunch of like magic bytes for PE executables just kind of littered through the kernel at various places. And so you'll run across something and it'll say MZ, and you say, all right, great, I found the kernel. And then you try and use that and everything is total garbage because that MZ byte is not actually the kernel. So you need to do a bunch more checks to make sure that you're not running across like either a fake header or an unintentionally fake header. I'm not sure which is the case. So once we know this is a PE, we know it's a NT version PE, so PE 32 plus, then we make sure that it has an optional header. We make sure the export header of the optional header exists and it has like a valid size. That's a good sanity check. And that's the point where there's no longer any fake stuff. So there are some fake structures that will satisfy the magic check for the DOS header, the NT header, the optional header, but there aren't any that'll satisfy that export header check. So once I got to that point, I didn't see any false positives pop up, which I thought was kind of interesting. That seems like a lot of steps to set stuff up if you're not doing something intentionally, but I'm making no accusations. So after that, then we find the name field of that export directory, which just tells other programs like what this program is. And we just make sure it's called ntosKernel.exe. And if that's the case, then you found the kernel, or you can be pretty sure that you have, unless somebody is really messing with you. We've got our kernel base address. Now, we don't know anything about what's in that kernel yet. We just know what the base is, and we know what the version number is, but we don't know where the structures are, and we don't know what they're called. So we need to get some debug info both for the kernel and for all of the applications and drivers running on the system. So we need to grab PDBs, and luckily Microsoft very helpfully has what's called a symbol server. So if you know some specific information about either a DLL, driver, or an executable, you can just download, if Microsoft has it and is willing to give it to you, you can just download the debug info for that file. Super helpful, helps a lot for debugging, and really helps us out for this because we couldn't do it without that information. So kind of similar process as before. We read the PE structure, and PEs have something called a debug directory. And some of those debug directories are in this CodeView 7.0 format, which apparently is PDB. Microsoft actually has an open source PDB specification repo on GitHub, which is archived and not being worked on. So maybe download that before it goes away, I guess. I don't know what the archive means. Then once we find that CodeView 7.0 information, there's a header for that specification that says, like, here's the file signature for CodeView, and then here's a GUID, or a globally unique identifier, which is just a string of numbers essentially, which uniquely identifies that file. And then there's what's called a file age. I don't know what this means. It's just a 0 or a 1, so I guess it's like not old or it is. And then there's a file name. So if we have all of that information, we can just download the PDB information for that executable. And then we can also just download a copy of the executable too, which is useful because it's actually not super efficient to copy executables out of a simulation, and you don't always necessarily want to do that. It's sometimes better to just download the fresh copy of the executable from the symbol server as well. And we can do that by knowing the executable file name, which for the kernel, we actually don't know until we check that export header, because for different distributions of Windows like IoT Core and ARM, there can actually be different kernel executable names that you might run into. So you actually do need to check this. You can't just assume it's ntosKernel.exe. All right, so once we know that information, we can download the PDB file, which has all of our debug information, and we can download the executable fresh from the symbol server. And this is what that process looks like. All right, so we've got executable image. We've got some headers. Those headers have information. This will probably be easier looked at like after the talk if you're really curious about it. Hopefully it'll be visible on YouTube. But the things highlighted in red, that time, date, stamp, size of image for the file header, and then the signature, age, and file name for that CodeView signature are the only things we actually need in order to get the debug information for our kernel. And that'll actually be true of all of the drivers and the executables running on the system. We just do this exact same process once we find the bases of all of those PE images loaded in memory. So we didn't actually need to do any extra work to find the PDBs for all of those things either. All right. So next thing we do, once we have the kernel PDB, we can use the base address that we already found for the kernel and the PDB info to figure out where in memory various structures in the kernel are. So one of those is the list of processes, very useful. And the other one is the list of kernel modules, also very useful. Those are actually the only symbols that I needed to use, but if you wanted to determine more stuff about the kernel from this, like I was only interested in getting base addresses for things for coverage purposes. But if you wanted to like analyze a system for malware and maybe like find kernel modules which are not in the list and figure out maybe if you have a rootkit running on your system, you might want to use more symbols in the kernel to figure out extra information beyond what I've done. So a little bit about paging. Basically, when a process is running, it's called paged in, and everything in that process is mapped. And then when you switch to another process, the stuff in that process gets mapped, and most, but not necessarily all of the stuff from the first process will be paged out. So if you try and access its memory location, there will be either nothing there, or it'll be something different because your current process has something else mapped. So because that's the case, there's some information specifically like the file names for processes that are paged out, which are not actually mapped for those paged out processes. And so it's kind of hard to build like a full list of the file names and all of the information and grab all of the stuff that we need to download PDBs for all of the paged out processes. So what I did is basically just said, all right, let's just grab it for the current paged in process. And then every time there's a change in the page maps, which is a write to control register 3 on x86, we'll just refresh and we'll just grab the new current process, unless it's the same as the old one, in which case we can kind of optimize and not worry about it. All right, so to get a process's information, basically what we do is we grab the, and this is for the current process. So we'll grab that kpcr, kernel processor control structure address like we talked about earlier. So we actually need this MSR whether we use the initial IDT method to find the kernel pointer or not. There's a couple other options for grabbing this address. We could also use a symbol in the kernel, which is the loaded processor list. For some reason, I had some trouble using the in-order process links from the kernel to find all of the processes. Wasn't able to like replicate it with other VMI systems on older Windows, so I don't know if something has changed in new Windows and that's not an option anymore, but I didn't explore it any further, so you can go home and double check my work. But yeah, so basically we read this MSR, grab the kpcr and therefore the kpcr RCB, grab the current K thread, which is the kernel thread information for a process that's running. That K thread has a pointer to what's called the E process, which is like all the process information. Like here's its priority, here's its process identifier, here's its name, here's, importantly, all of the modules that are loaded in that process. So there's a linked list for each process that has all of the modules loaded into it. And that's like if you have a exe and it loads 50 DLLs, all 50 of those DLLs will be in that list. So that's this one. I actually think the graph is a little easier to look at. So we go from register to kpcr to kthread to eProcess. We need to grab that field directory table base because that's actually the base of the page table for the current process. So we need that actually to do the address translations. So once we have that address translation information, we can grab all of the rest of these fields using that address translation, because otherwise we would just get like garbage because it's not paged in or mapped. So we grab the file name, we grab what's called the PEB, and then over there on the right you can see that arrow points back to itself. That's just a linked list of all of the modules for the process. That gives us our file name, our like PDB GUID information that we need to download the debug info for that module. And we need to do that for every process once we see it. In order to have like full coverage of it, because very frequently the actual executable is going to be pretty small and most of your functionality will be in DLLs. All right, so once we've done that, we'll have like the DLL base address for all of the modules loaded in the system. We'll have the entry point, we'll have the image size, and from all of this, we can Sorry, I'm kind of running out of time, so I'm going a little faster. From all of this, we can build lookup trees. So basically, for all of our modules, we take the debug info, and we get all of our symbols. From all of those symbols, we have a base address of that symbol and a size. And so from that, we can construct a range, which we can use whenever we have a program counter during our execution. Remember, that's all our fuzzer really knows is program counters. We have that program counter. We can figure out what range we're in of addresses, which will allow us to look up the symbol. And from that symbol, in PDBs, each symbol has a list of lines. And those lines also have base and size. And we can look up our address in those ranges of lines as well. So just using our program counter, we can now say what line of code are we on, what function are we in, and that's actually all of the information that we need to construct that LCOV coverage, which will give us that really nice displayed graph or listing of code for our users. So I used interval trees for this, which is a nice data structure for range lookups. It's really great for a lot of reverse engineering program analysis type stuff where you're doing similar PC to something lookups, because they're almost always ranges. And basically what this is, it's like a specialized B tree where you have linked list lookups, and you get really efficient queries, which is nice because querying is most of what we're going to be doing. We only build the tree once every CR3 write, but we have a query every instruction that we execute. So it's a ton of queries. So log of n is really good where n is just the number of intervals, which is not actually that big. You'll have maybe a couple thousand lines that you need to look up over. All right, so from there, we correlate the coverage back from the PC. All we need to do is subtract the PC from the base address that we know we're looking at. Or we can do what I actually did, which is just store the lookups as PCs instead of offsets from base addresses of program objects. And that way you can just directly go, all right, PC, what's the range I'm in? Give me the line and symbol coverage. We build that into our fuzzer. Every time the system sees a write to CR3, we reload those ranges. And then we write that out after fuzzing's done to LCOV, and we have HTML coverage of all of our kernel code that we've been fuzzing. So Google search, it's kind of okay. You really need to know your search terms. And so it's really nice to find a forum or a Discord or somewhere where people can tell you, here's some actual information instead of AI-generated garbage. And then once you have that, you can actually find the stuff that you're looking for. GitHub search, which I kind of use to search through volatility and libVMI libraries, is currently amazing. Make sure you log in, and then if you learn how to use the search terms on GitHub search, you'll be able to find almost anything instantly. Ask Game Hackers stuff. They love to talk about the cool hacks that they've done, and they'll just walk you through everything, even if they didn't post code with comments. And yeah, be lazy. Don't reverse engineer anything. I didn't reverse engineer Windows at all for this project, and I don't really think anybody should do it because so much information about Windows is public that unless you're really looking for exploits, I don't think there's any reason to try. So, yep, that's it. Questions? I think we have 10 minutes, right? Oh, all right. Well, I have a flight to catch, but if you want to follow me on stuff, you can send me messages later, and I'm happy to help with any of this related things. But otherwise, thank you.